Welcome back to everybody. So we have the closing talk of the workshop, and it's an honor for me to present Professor Cockburn, Bernardo Cockburn of Minnesota, of the University of Minnesota. The title of his talk is Symplectic Hamiltonian Finite Element Methods for Wave Propagation. Please, Bernardo.
Yeah, thank you, Alexandra, and again, I'm very happy to be among my Italian friends, you know, and I have to thank the organizer for being so accommodating and bypassing my neglectful answering. So thank you very much. So is it okay this way? It's okay this way?
Yes, we can see.
Okay.
It's okay, it's okay, perfect.
So I'm going to talk about this symplectic Hamiltonian finite element method for wave propagation. This is joint work with Manuel Sanchez, who is a former postdoc now in Santiago de Chile, and with my collaborator from MIT, Kirk Yuan and Jaime Pereira. So here is the idea of the sketch of the talk. First, I'm going to show the problem. I'm going to show you three model wave equations, and I'm going to write them in three different ways. In particular, I'm going to write them as symmetric hyperbolic systems and as Hamiltonian systems. And then the question is going to be for what kind of formulation is better to discretize. And then I'm going to give the main idea to proceed for the discretization. And the idea has two ingredients. One is the symplectic method, and the other is Hamiltonian machinery, which I'm going to describe in number 2 and number 3. And then I will very briefly say how to combine these two things to create these symplectic Hamiltonian methods. I'm going to say something very quickly about previous and related work, and then something about what we are doing nowadays. So we are interested in devising as systematically as possible fully discrete numerical schemes for hyperbolic problems, which are high order accurate and preserve not only the energy of the system, but as many as possible other physical quantities of interest. And the emphasis here is when long-term simulations are sought. So we are currently developing an approach to achieve this for hyperbolic problems with Hamiltonian structure. We cannot do that for any hyperbolic problem at this point, but we are using the fact that the structure of the hyperbolic problem is Hamiltonian. And here we are going to consider the case of linear wave propagation model problems. Okay, so here we go. So we have the wave equation, we have the acoustic wave equation, the elastic wave equation, and the electromagnetic wave equation. And I have written them in three different ways. On the top, you see two derivatives in time, and in the rest of them, you only see one derivative in time and one derivative in space. If you pay attention to the red row, you will realize that these systems can be rewritten as linear symmetric hyperbolic systems. So that's the structure of this method. They are linear hyperbolic systems, symmetric. And if you go to the third line, the blue line, these methods have a different structure, and the structure they have is Hamiltonian, as I am going to show. So the question is, I personally don't like more than one derivative, so trying to do something about the first formulation is out of the question. So now the issue is, should I use the symmetric hyperbolic formulation, or should I use the Hamiltonian formulation? So the issue here is that typically when you use your favorite DG scheme, a discretization of a system that is of a set of equations that is written as hyperbolic symmetric system, it typically produces a dissipative scheme. This is this is not a good approach, and so we decided to instead try to explore the Hamiltonian system, and we are going to show that new digit discretizations of each of these three wave equations can be obtained, which produce a non-dissipative scheme, which also can provide non-drifting approximations to invariant functionals. So that's what I'm going to talk about today. And let me give you an example. So this is I'm going to compare DG method that is dissipative, which is here for the acoustic wave equation. This is the displacement, this is the velocity, and that's Q. And then I'm going to compare this with the new DG method, and they are of the same accuracy, but as you see, this method is non-dissipative. So the blue guy is non-dissipative method, and the red guy is the usual dissipative DG method. And you can see that you can see the effect of the dissipation here. Here, I think we have done like 100 cycles around this domain, so you can see the effect. And we are using polynomials of degree 5 here, something like that. So you can see that the dispersion is also smaller. This guy is going backward, whereas this guy is going forward for this particular wave. Well, they are kind of essentially the same, but the importance is that the amplitude is not decreased. And I can show you also the energy. The energy is conserved, as you can see here, and for the new method. And for the old method, this is the ratio of the difference over the energy. You see the energy decays until it kind of becomes 1. So this is the difference between the energy and the discrete energy. So you can see here the effect of the dissipation of the energy, and here the fact that the energy is maintained constantly. And we also have plotted here this highly oscillatory part of the energy. And if you add to this energy the energy associated to the inter-element jumps, you get the energy that is in the round, the little balls there. So you can, independently of how do you pick an energy, you can have either a constant energy or an approximate energy that doesn't drift. So this is what this method can achieve for you. And the main idea is the following. So first, or second, as we are going to see, first you discretize the Hamiltonian system that you have in space, and you make sure that the resulting system of ODEs is also Hamiltonian. And why is that? We want to have a Hamiltonian system so that we can apply to it a symplectic time matching scheme because the application of symplectic time marching schemes on Hamiltonian systems ensure non-drifting properties of the Hamiltonian, for example, and of other first integrals of the system. So it's like preparing instant coffee. You have your coffee in your jar, and you have hot water. So hot water is the symplectic time marching schemes, and the coffee is a Hamiltonian system. So you just put them together and you get the scheme you want. All right, so that's that. So let me first talk about the symplectic time marching schemes. I suppose that this is not a widespread and popular topic, so I'm going to say something about symplectic time marching schemes and why they are interesting. So these symplectic schemes were I believe, introduced for the approximation of Hamiltonian systems. And the easiest Hamiltonian system we have is the following. This is a 2x2 system. P dot is equal to this derivative of the Hamiltonian, and Q dot is this derivative there. And H is called the Hamiltonian. And we can immediately see that the orbits of the system, when you evaluate the Hamiltonian at the orbits of the system, the Hamiltonian remains constant, because you take the time derivative of this and you get the formula, and P dot is exactly this guy with minus, and Q dot is exactly this guy plus, so this is 0. So for Hamiltonian systems, you know that the Hamiltonian is constant on the orbits, or in other words, the orbits lie on the level sets of the Hamiltonians, the level curves of the Hamiltonians. So now what I want to do is to see what happens if this system is discretized by a symplectic method, and I'm going to take the most simple symplectic method, which is the symplectic Euler method. And you see that this is a discrete version of the first equation, and this is a discrete version of the second equation. And what is interesting to note is that the method is implicit in Pn, but is explicit in Qn, right? It's explicit in P here, this part, but is explicit here. Now, if the Hamiltonian, if the derivative with respect to Q of the Hamiltonian is independent of P, then this term depends on Q, and this Euler method is fully explicit. Okay, so what does mean that the method is symplectic? Well, it means that the area in the phase space is remains constant on the iteration. So I take this wedge product of this differential form, and this gives me the differential of the area at the iteration n plus 1. And here I have the differential of the area at the previous time. And this is, of course, given by the flow defined here. So what happens is that the area in the free space is the same. This means that the method is symplectic. And the interesting thing is that this particular property implies that there is a discrete Hamiltonian which is close to H, such that the Hamiltonian, that all the points of the flow lie on the same level sets, right? So if I evaluate this new Hamiltonian on Pn plus 1, Qn plus 1, I get the same value as evaluating at Pn, Qn. So in this sense, when I approximate a Hamiltonian system, I'm approximating this Hamiltonian system by a symplectic method, I do get something that has some kind of a Hamiltonian structure, in the sense that all the points lie on this level set. So let me give you an example. Suppose that I have the harmonic oscillator, and that's the simplest quadratic Hamiltonian, and we can easily find that this is true if and only if we have the formula. So the new Hamiltonian associated to the symplectic Euler method is equal to the old Hamiltonian minus delta t times p cubed. So this means, this is interesting because, first of all, we know that this is going to happen. So for all times, this is going to be a constant. The constant is equal to the value that this has at the very beginning, as I put here. And so you see that at some point, PQ can be positive or PQ can be negative. So the value of this guy as n increases is going to be either bigger or smaller than h. So this is what is meant when people say that the approximate energy or the approximate Hamiltonian does not drift. It oscillates around the correct Hamiltonian. And this is what we have seen here before in the example I gave you here. You see these oscillations are precisely this what I was referring to. Okay. So so what can we say about the symplectic method? There is a vast literature on symplectic methods, and I recommend the 92 review by Sancerna in Acta Numerica. We are particularly interested in symplectic Runge-Kutta methods, which are unfortunately diagonal, implicit, but they have very nice conservative properties, and they were characterized in '94 by Bochev and Scovell in DIT. For separable Hamiltonians like the one we have for the harmonic oscillator, there is another class of methods that are called the explicit partition Runge-Kutta methods that are actually very efficiently implementable and are symplectic when they are applied to separable Hamiltonians, as was shown in this 93 paper by Abia and Sancerna in NatCon. So essentially, if you have something that has Hamiltonian structure, you just want to go to the shelf and pull your favorite symplectic method to solve if you want the energy to be conserved for a long time. So now what I want to do is to show you the second ingredient, which is the Hamiltonian machinery, and I'm going to explain this in the framework of linear elasticity. So I'm going to write this in terms of linear elasticity, electrodynamics, and so here we have to introduce the machinery, and so we start by saying that the mappings, the orbits, these are orbits in a smooth manifold M, and it defines we say that it defines a dynamical system which is Hamiltonian if we can rewrite the equations that define the orbits in this way. So this is C dot, and this C is some special functionals which are called the coordinates functionals, and they are defined on the phase space, and they can be identified with the so-called test functions, as we are going to see. I know this is a lot of notation, but I'm going to give an example soon. H is the Hamiltonian, and these brackets are called the Poisson bracket, which is a bilinear antisymmetric form which satisfies an identity called the Jacobi identity. So for the moment, that's not really important. So if we have this, we call the triple M, the Poisson bracket, and the Hamiltonian, a Hamiltonian dynamical system. So what I want to show you is that these equations here, they do define a Hamiltonian dynamical system. And so what we have to do is to define C, H, the Poisson bracket, and M and tau. So the Hamiltonian is nothing but the energy. So we have this kinetic energy, and this is the strain, the elastic energy, and something about the boundary conditions and the forces inside the body. The Poisson bracket is this simple expression here, where these deltas, they represent functionals, the functional derivative of the functional f and g. And f and g, they depend on u and v and not on t. So that's the Poisson bracket. The phase manifold is just a set of functions in L2 such that this quantity is in L2, and we satisfy the boundary conditions. The Dirichlet boundary conditions are imposed in the space, and this is so this is essentially I believe this is Q and the other is U, something like that. And the coordinate function are these functions. These functions are infinity with zero boundary conditions. They correspond to this. So now we have to do a little computation here, and we take the time derivative of this guy. This is equal to this. This is by definition equal to that. This is always true, but this thing by definition is this functional derivatives, and then you can prove that a little computation gives you that this is equal to that. And so we have that rho u dot phi is equal to v rho v phi dot for every phi. So this means that u dot is equal to v. So this gives us the first equation. And the second equation is obtained in a similar manner. So you start with this guy. This is equal to c dot. This is given by that, by definition. And then you use the definition of C and H, the Hamiltonian, to obtain this thing. And this gives you that the second equation is satisfied. So this means that by definition, the equations of linear elastodynamics define a dynamical system. They have a Hamiltonian structure. So how about conservation laws? Suppose that we are taking this conservation law. This is my linear momentum. So I dot this linear momentum, the total linear momentum, against a constant vector. And I can write that this J is equal to one of the coordinate functionals times phi. And we have seen that this was already 0. So this proves that the conservation of the linear momentum in time is satisfied. And we can also do the same thing for the angular momentum and for the energy, because in particular the energy is very simple to see. H comma H is equal to 0 because this is antisymmetric. So maybe this is difficult to follow, but the point is that once you have that the system has this Hamiltonian energy, you can obtain a lot of properties right away using this structure. So, so what do we do? To define our approximation, what we have to do is to mimic exactly what I have shown, and get a discrete version of that. So we discretize the equations of electrodynamics by using weak formulations of the original equations with your favorite method. And then you have to prove that the orbits define a dynamical system which is Hamiltonian, and this means that we can have this property for all sorts of functionals. I call the coordinate function and h, and then they define the original weak formulations that we are using to define the method, and so this thing is a discrete Poisson bracket, and we have to show that the triple is a Hamiltonian dynamical system. And it turns out that this part of the job is extremely easy, so I'm not going to present that. It doesn't represent any major difficulty. So now we can combine these two things together, and so the idea is that you start with the set of PDEs with Hamiltonian structure, and you discretize them in space so that you preserve some Hamiltonian structure, and then you apply on top of it any symplectic time marching method. And this is what is going to give you the desired stuff. So let me give you a simple example. This is a P wave, a compression wave going from left to right, and we have let this go like 100 cycles. This is a P wave. This is an S wave, so it's going to the left and to the right, and moving forward. And this is the energy of the first, and this is the energy of the second. And again, this part of the energy is the energy with the jumps, with the energy of the jumps, and this is without the energy of the jumps. So you see that there is an oscillation, but there is no drift, just as we wanted. So that's what I wanted to show you guys. So let me very quickly tell you that the idea of using these symplectic Hamiltonian methods with finite difference and finite volume methods is very old. In fact, Yee's 66 famous scheme for Maxwell's equation actually uses the symplectic Euler method. This goes a long way back. When we discovered this method, we were excited because we thought we were the first, and then we started to see, oh, this guy has done that, and then before them, and there was this plethora of people that had done before us a lot of things. The interest in using finite element methods for SH methods is more recent. I believe that the first paper that did that was in 2008 by Yang Xu and collaborators. They used some DG method for Maxwell's equations in 2D. And then in 2015, we found a paper by Kirby and Kuer on mixed methods for elasticity. In 2017, we did the first SH HDG method for the acoustic wave equation, and then in 2021 we extended that to linear electrodynamics. So these are the results I show you, and I have to mention a new DG method for symmetric hyperbolic systems that achieve exact conservation for any symmetric hyperbolic system that was uncovered in 2019 by Fu and Chiwan Shu. So these methods are quite different in structure. They use Lax-Wendorf type time matching schemes, and they usually have to double the number of unknowns. So they apply to any symmetric hyperbolic system, not only to those systems with Hamiltonian structure. And then the thing that we are doing nowadays is to study the equations of Maxwell, and then extend this to nonlinear solid mechanics and nonlinear water waves. That's it.